Okay, well, hello everyone, and thanks to the organizers for inviting me to this lovely venue. I'm judging by this, so I'm trained as a quantum many-body physicist, and I'm judging by this morning session that I'll be assuming things that you maybe don't know about. So I'd much prefer you to interrupt me during the talk if you have any questions, and rather than sit there unhappily till the end. Okay. So as we just heard, there's been quite a large recent theoretical effort to revisit quantum dynamics. And the dynamics of many-body quantum systems has been studied now for decades, starting in the 60s and 70s. And you might ask, well, why revisit it? We've been studying it for a long time. And the point to make is that unlike real materials, real condensed matter materials, today's quantum devices operate in a very different regime. So a lot of that old-fashioned theory is about ground states. It can be near equilibrium. So you're taking a thermal state and you're just perturbing it weakly. These devices, they are almost inherently far from equilibrium. You start with some state that is very far from equilibrium, and then you hit it with either Hamiltonian evolution or even a set of unitary gates. And this dynamics might not be native to any material that we realize in nature. And in particular, it transcends the familiar Hamiltonian time evolution that we learnt about as undergraduates. So this is why these devices have actually thrown up a whole new range of dynamical regimes that are actually new to theory. We don't really have good conceptual tools for dealing with a lot of the dynamics that you encounter in these systems. So how do we probe dynamics? How do we classify this vast array of possibilities of dynamical behavior? Well, there is the kernel of dynamics in a way. The simplest thing that you can have is hydrodynamics. So this is at long times and large wavelengths, what's left over. So in a generic system, at short times, you have this very fast relaxation, and what's left over is the splashing of a few slow modes. So I like to take on this slide, I like to take a picture of a local body of water, and here we have the Rhine as seen from Mainz. And you can see from the smooth surface of the water that if you perturb it weakly, that response is going to be described by just 5 equations. So these are, of course, the Navier-Stokes equations of fluid dynamics. You have 1 equation for particle density, 3 for momentum, 1 for energy. So 1 equation per conserved quantity. And all that you need for this simplification, this vast simplification from Avogadro's number of particles to just 5 equations, is a separation of scales. So you need the length scale for microscopic collisions to be much smaller than the length scale at which you're probing the system. And you also want a non-zero temperature, so your degrees of freedom can relax efficiently within each fluid cell. And given these 2 constraints, hydrodynamics should apply. So in our early education, we come across a lot of examples of hydrodynamic theory in real materials that may not actually strike you as hydrodynamics because they're too boring. So the classical example is, of course, Fourier's law of heat conduction, possibly the oldest such equation that was written down, soon followed by Fick's law of diffusion. These are canonical classical examples. In quantum physics, we have the Drude-Sommerfeld theory of electronic transport. Again, you might not think of it as hydrodynamics because it's too simple. A slightly more advanced formulation of that is Landau's Fermi liquid theory, which I will revisit again. But for essentially this reason that these equations are boring, hydrodynamics in condensed matter systems, I think, used to be thought of as boring. The point being that in a lattice model at non-zero temperature, you only expect, say, energy, charge, and spin to be conserved. There is no interesting dynamics, just these diffusion equations, and it's more or less been known for centuries. So part of what I want to get across in this talk is that quantum devices can realize much richer regimes of hydrodynamics, and I won't have time to describe these particular examples, but some of which were not anticipated or foreseen in condensed matter counterparts, and have actually motivated us to revisit condensed matter systems and look for this new physics. Okay. So you might ask, well, why do artificial quantum systems have interesting hydrodynamics that we couldn't realize before? And the reason is that in real materials, these additional slow modes that might lead to interesting behavior beyond those standard conservation laws, they're quite hard to see because you have realistic imperfections like disorder, phonons, substrates that prevent you from seeing these behaviors at long times. So how do I get anything beyond the standard package of energy, charge, and spin? Well, the simplest example is actually a gas of free particles. So if you think of a gas of free particles in a box, how would you describe it? Well, actually, all of the individual velocities are conserved up to reflections off the boundary, and you can think of each velocity as a conservation law. So in this sense, the gas of free particles has a lot of conservation laws, in fact, an extensive family of them. So the hydrodynamics, it's the free Boltzmann equation, and actually that's an infinite number of hydrodynamic modes in the thermodynamic limit. So free systems have a very different kind of fluid dynamics from what we're used to in real materials, but they're kind of trivial, right? It's almost a trivial counterexample. There is a class of non-trivial counterexamples known as integrable systems. These are genuinely interacting systems which still conserve some asymptotic velocity parameters. So they, like free systems, they also have infinitely many conservation laws, but they're also somewhat non-trivial in that they involve even physically realistic interactions. And the reason that these are worth, for a long time, these systems were thought of as kind of a theoretical abstraction. But in the last 20 years, we've seen a lot of artificial quantum systems that are actually close to being integrable, in the sense that they're interacting and that yet they have many conservation laws. And so they have additional slow modes and more exotic hydrodynamics. And if you had a traditional condensed matter education, okay, so for those of you with a traditional condensed matter education, you should think of either Luttinger liquids in one dimension or the phenomenon of zero sound in more than one dimension in Fermi liquids as realizing this near integrable regime. So the Luttinger liquid for concreteness arises in 1D spin chains in carbon nanotubes at very low temperature. And similarly, zero sound is one of the defining features of liquid helium at low temperatures. And both these systems natively exhibit many conservation laws, many more conservation laws than the naive hydrodynamic count. Okay, so in the references, I discussed some examples of this kind of phenomenology. But one thing, the subject of this talk is that actually sound is special too. We don't think of sound as being special, but unlike conventional heat, which just diffuses, sound spreads ballistically. So it spreads much faster than heat, and you might wonder why this is. It's because ballistic modes are special. They require extra symmetry. So I just talked about this extreme case where you have infinitely many symmetries, infinitely many conservation laws, and infinitely many hydrodynamic modes. Sound is much more modest. It just needs one symmetry, which is translation symmetry. Now, this special feature of sound means that actually we don't tend to consider it when we're doing condensed matter physics, because in a lattice model of electrons, the crystal lattice breaks translation symmetry and you don't have any sound. So it's only in these very recent experiments that realize ultra-pure 2D metals that we actually have observed a regime of electronic sound, but generically we don't expect them in a lattice model at high temperature. So the main point of this talk is to show you how it's possible to get long-lived sound modes that are on a lattice, so there's no momentum conservation. They're in a chaotic system, so there are none of these special features leading to extra conserved quantities. And it's at high temperature, so low temperature can't suppress scattering for you. And if I relax any of these conditions, it's easy to get a long-lived ballistic mode. If I impose all three of these conditions, you really don't expect anything resembling sound. So in a way, forgetting the rest of this talk, this is the most important slide, so please let me know if you have any questions at this stage. Yeah. Extensively many conserved quantities. However, they can be from beta ansatz, fragmentation, MBL, yeah, whatever, yeah. Anyone else? Okay, good. So this is now the main part of the talk. So why were we thinking about this in the first place? Well, this project actually was born from looking at some experimental data from the group of Wasim Bakker at Princeton, which realized a Fermi-Hubbard model, which you saw a one-dimensional version of in the last talk. I will describe the model in a second, but it's basically hopping plus density-density interactions. They were looking for what's called bad metal physics, a particular signal in the resistivity at high temperature. And the way they looked for this is, what you see on the left is they initialize basically a charge density modulation, and they just let it relax in time. And they plot the contrast as a function of time. And what you can see on the right-hand side is how this contrast is decaying in time. So the red curve is when I take a very long wavelength charge density modulation and I just let it relax. I look at how its amplitude decays in time. The blue curve is when I go to shorter wavelengths, I do the same thing. And what you're seeing is that at the longest wavelength, you get this nice conventional hydrodynamic behavior with diffusive relaxation. But at the shorter wavelengths, this blue curve, you have this funny wiggle. That's so you're seeing a crossover from essentially underdamped decay to overdamped decay as you increase the wavelength. And I found this quite surprising for the reason that this was experimentally advertised as a hot, chaotic lattice model. So it's the 2D Fermi-Hubbard model. It's chaotic. It's at high temperature. It's about, let's say, 40 by 40, order 100 by 100 atoms. It's really a lattice. So you expect normal diffusion. And the question is, how is this underdamped sound mode surviving? So that is what motivated this investigation, is trying to explain systematically what's causing this blue curve here. So why shouldn't there be a sound mode? Well, it's simplest to think about this in a 1D Hubbard-like model where I just have interacting spinless fermions. So H0 is some hopping term, fermions hopping between sites, and this interaction V is what makes the system chaotic. It's a density-density interaction between sites. This model conserves charge. In fact, you can prove just from the Heisenberg equations of motion that there's a lattice version of the continuity equation. So there's an operator conservation law, that's equation 2. So that is one hydrodynamic mode. But the point is that the current, the total current of the charge, generically decays at long times, and that is why there is no sound mode in the system. And this is true in 2D as well, and so this is why I was surprised by that underdamped mode. So to try to isolate this effect, what we thought we would do is take this charge current and try to make it decay as slowly as possible, in the hopes that you're going to evade normal diffusion and get some long-lived ballistic mode. So it's the slightly funny variational problem we're actually solving in the space of all possible Hamiltonians. So we're trying to minimize the current decay subject to fixing the current size and the interaction strength over all possible Hamiltonians of the form I just showed you. And what this is going to do is it's going to force slow decay of the current, but in a genuinely interacting regime. And because of the way I've set up the problem, it ends up avoiding the trivial solutions of no hopping or no interactions. Rather surprisingly, for nearest neighbor hopping, this turns out to be solvable. So you can actually, if you decide to cut off your allowed range of interactions by hand, that's capital R, for any given range of density-density interactions, you can cook up a model that has a decay of current that is as slow as you want. So these numbers in this table are for any given interaction range, the strength of density-density interactions at range 1, 2, 3, 4, and so on. And here you have the decay rate of the current getting arbitrarily slow as I allow the range of interactions to increase. Does that make sense? I will assume that it does. And so we've cooked up these models that we claim have this kind of sound mode, and the question is, do they actually have this behavior? So what we did to probe this was to do numerical simulations that mimicked the experiment as far as possible. So you start from a density matrix that represents essentially a weak density modulation at very high temperature. In fact, we're perturbing about infinite temperature, and we're adding just a small texture of charge, which is what the experiment was actually advertised as roughly being in. And you can evolve this under standard Schrödinger evolution and look at the lowest Fourier mode of the charge density. And that way, we're going to try to reconstruct the plots that they had. And you see that actually these models do pretty well. As I increase the allowed range of interactions and take down this current decay rate, I'm starting to recover this underdamped phenomenon that the experiment saw. And this is just exact diagonalization on 14 sites. So I'm taking the exact spectrum of the quantum system and really simulating this. What is? Oh, it's the strength. It's the contrast of that wave number, of the initial wave number. So it's the amplitude, if you like, of the texture. So I initialize at Q and I probe at Q, and that contrast decays. This is at the very longest wavelengths. So, yeah. So why is this happening? Well, it turns out that if you try to describe the kinetic theory of this model semi-classically, what you find is that it has quite a peculiar form, which is this phase-space hydrodynamics. So it's not. So what's going on here? On the left-hand side, you have a standard Boltzmann streaming term, position and velocity, and you're just freely streaming at whatever your velocity is, just like free particles. But on the right, you have this localized diffusion in momentum space. So this is how the system manages to be chaotic and yet have this unusual hydrodynamics. It's got very strong scattering, but that scattering is local in momentum space, and that's why you have this strange hydrodynamics. Really, the hydrodynamics is happening in phase space. It's not happening in the usual way of conserved quantities. And so if you just try to diagonalize this kinetic equation, you look for you solve it with some basis of normal modes, let's say, you actually find that depending on the wave number at which you probe the system, you see more or less underdamped modes. So the very smallest Q, the truly hydrodynamic regime, is over here. And there, indeed, you have a single underdamped mode, which is just the charge. But what you find is that as you increase the wave number, these modes are colliding, and you're getting more and more underdamped modes as you probe the system at different wave numbers. So this is very peculiar, because what we end up seeing in practice is that we get the hydrodynamics of almost an integrable system, but it's a microscopically chaotic system. So for example, here, it might look to you like you have four underdamped modes, even though you expect 1 from a naive count of conservation laws. So this is very peculiar, because what we end up seeing in practice is that we get the hydrodynamics of almost an integrable system, but it's a microscopically chaotic system. So for example, here, it might look to you like you have 4 underdamped modes, even though you expect 1 from a naive count of conservation laws. Yeah, so we think this effect might be relatively generic in the sense that the only physics required is this slow diffusion in momentum space. And what that's going to do is confound your naive expectations of what the hydrodynamics should look like. And once you diagnose that this is what's going on in at least the models we cooked up, it connects it both to related phenomena in integrable systems and actually in 2D metals. So there were some very nice recent papers pointing out that 2D metals also have a regime where the scattering is highly localized in momentum space, and we suspect that some of the effects they are predicting in those papers are related to what we're seeing, but that's work in progress. For now, we think the most pressing questions are sorting out a precise quantum classical correspondence. Because the explanation I gave you for what's going on is pretty semi-classical, right? I wrote down a Boltzmann equation, but on the other hand, I was simulating 14 spins. So we want to somehow bridge these highly quantum simulations and this very classical reasoning. The second thing we'd like to do is to develop sharp experimental diagnostics of whether this slow momentum diffusion is really what's going on. And I think this would be useful in conclusively proving this regime in 2D metals as well, where it's largely so far just a theoretical prediction that they should have similar physics. Finally, I want to mention that the specific kinds of Hamiltonians I wrote down are actually most likely to be realized in the near term in systems of trapped ions, where you can actually tune the hopping and the interactions in such a way, in principle, as to construct these optimal models. Okay, so with that, thank you for listening, and you can see the preprint for further details.